Good, thank you, Alpha. Well, as you can see from the slide here, my name's Mark Whittle. I'm from the University of Virginia, which you'll notice is a long way away, which means I'm a little bit jet-lagged this morning, and I apologize. I'll try and, keep lively and focused. I'm delighted, actually, to be here. I realize the talk you're about to hear is going to be quite different, I think, from most of the other lectures in this course. I looked over the syllabus, and it's very rich in philosophy, literature, history, and there's 2 lectures, I think, devoted more to sort of modern physical science, and in particular the theme of evolution, maybe. So this lecture and the next, on Wednesday, are going to pick up the concept of change in the universe in 2 different ways. Today's lecture, I'm really going to focus on cosmic evolution, and in particular the birth and growth of things called galaxies, which I'll introduce to you in a moment. And then Wednesday's lecture, I'm going to pick up that story much more locally and talk about the birth of stars, including the sun, the origin of the development of life on Earth, okay? Something else that's going to be different about this lecture is that the subjects, both of sort of cosmic evolution and life's evolution, are now extremely well developed and very thorough and rich, and it's not possible really for me to give a complete overview of them. So I'm going to be dipping in. You're going to hit the highlights, I think, or at least, I don't know about the highlights, but at least specific points of the story, and I'm afraid I have no time at all to deal with the history of the development of this subject. This is not going to have any historical component. I'm going to just jump straight in and try and tell you, as best we currently understand it, the nature of the universe and the nature of its change and evolution. Okay, so with that said, let me first of all test whether this works. It does, good. So I'd like to introduce you to, or perhaps remind you of, some of the components of the universe which are immediately outside our realm of immediate perception. And I think the best and most effective way to do that is to take you on a trip quickly. In 3 minutes, we're going to traverse 20 million light years, which means that in effect, we're going to be traveling at over 1 trillion times the speed of light. This is a scientifically accurate, but nonetheless artificially created movie, and it's going to begin with a view from the Earth. Okay. I think for this movie, can we kill all of the lights? All of these lights down. Because the surface brightness of the projector, thank you. True, stay awake, folks, and I'll bring the lights back up in a moment. So this view from the Earth, actually you may recognize the belt of Orion here. So this is more or less a view from the Earth. Let's just start the trip now, and I'll stop it at various points. So here we are speeding away from the Earth, and you'll notice a few things. We stop it there. So first of all, there are stars, which are, of course, we're about to pass by many of them. You can see here, that's somehow just come off. Let's stay there. So this region here is the Orion Nebula. Some of you may have seen it in a small telescope. It is a star birth region. It's a maternity ward for stars. There are currently about 1,000 stars being born there, and about 5 million years from now they will be born. They're in the process of being born. This is the theme I'll pick up at the beginning of the next lecture when we talk about the birth of stars. So let's carry on. We'll just actually go through it, I think. The young stars are actually the biggest, brightest ones are right there. There's a slightly more distant nebula called the Horsehead Nebula in Orion. Remember, of course, we're zooming along at enormously superluminal speed here. It's not physically possible to do that. Right here is the end product. Oh no, excuse me, that's about to be there. That's another star birth region called the Rosette Nebula. We keep zipping past the stars. I know probably this is familiar because it looks like a scene out of Star Trek, and that's because Star Trek pays attention to what astronomers have discovered, and so they make it lifelike and real-like. This is the other end of the star's life. This is the death product of a massive star. It's called the Crab Nebula. About 1,000 years ago, a star exploded there. That's another topic I'm going to pick up next time, because the guts from that star go back out into the interstellar medium and get added to the material which will birth the next generation of stars. So now you can see the view has begun to lift up out of this enormous system that you see we're part of. And this is called the Milky Way, is our vision of it, a band across the sky. Now we're lifting up and we see it for what it really is. It's a galaxy. This is the name of the thing, called a galaxy. And as we get higher, we can really look at its structure, morphology, as one would say in astronomy. So it has this beautiful spiral pattern. Again, this is attempting to be scientifically accurate, so we do think we have some sense of what the pattern looks like, what the colors look like. We just came from a region down here, approximately. We lifted up from the region. That's where the sun and the solar system are. So let's carry on now and begin to take in the extragalactic scale. Extra here means outside the galaxy. You'll notice that we have a couple of dwarf galaxies that are in orbit about our own, and here's another local group galaxy. Every other dot that you see here now, these are no longer stars in our own galaxy. These are other galaxies, entire systems rather like this one. I'm going to come to the size of this in a moment. You can certainly sense its motion. It is indeed spinning. It takes about 200 million years to make one twist. So in its whole lifetime, it's undergone about 40 or 50 twists. It's sort of middle-aged in the sense that the twist would be 1 year, would be a metaphor. So let's carry on now. Our vision sweeps around. You can see other galaxies in the background. Here coming into view are two big principal sister galaxies, if you like, or brother galaxies. This one's called M33. It's a rather flat spiral galaxy. We're going to go right through another starburst region here. We're going to zip through that. And then we bring into view this very famous galaxy, the Andromeda Galaxy. It has a couple of neighbors as well. Okay, our agenda in this trip is to converge down here on a huge cluster of galaxies, of 1,000 galaxies, but we're going to join, we're passing two interacting galaxies there. They're close enough together to be interacting. I'm going to return to that theme later on in the lecture. We pass by the Whirlpool Galaxy here, and its little neighbor. There's another mildly interacting pair of galaxies. We're joining several hundred galaxies in a column here. There's a big, thick tube of galaxies that are falling towards the great Virgo cluster of galaxies. These are building the cluster by falling downhill, down the gravitational slope, into this great region where matter is concentrated in the form of about 1,000 galaxies. We're heading, in fact, for the central galaxy, this one. It's called M87. There's a couple of interacting ones there. We're going to zoom right into the middle of it, and that'll end the journey. We've made our trip 20 million light years in 3 minutes. And here we are at the center of the giant galaxy, about 10 times more massive than our own galaxy. You'll notice a little blue streak there coming. It's a jet that's been blown out by a 3 billion solar mass black hole that's sitting at the center of that galaxy. I'm afraid that's a piece of the story I'm not going to have time to talk to you about. Never mind. Galaxies have many interesting properties. Having big black holes at their center is one of those properties. Okay, perhaps we could have the lights of the main auditorium up, but not the front lights, just the main. No, not these guys. That's great. Now, these ones you can kill. Thank you. That's great. Thanks. Now, I just forgot to do something I wanted to do, but never mind. So I want to give you a sense of scale. So that beautiful spiral galaxy, our own Milky Way galaxy that we came up out of the disk of, I've now mapped onto a region here. You'll see why in a moment that I've placed the center somewhere in Italy, and we go all the way from Turkey out through into the Atlantic coast of Portugal and Spain. And so this is going to be a scale model, and I want you to imagine now this has 100 billion stars in it, and what I want to do is to place the sun and the solar system on this model with an appropriate scale. And to do that, I'll just bring up that scale, and I realize now Alpar was quite correct in telling me that this was going to be a completely pathetic demonstration, but you'll notice I have in my fingertips here a pin and a pinhead. That is the orbit of the Earth in this room in Istanbul, and the Milky Way galaxy spans the region from Turkey to Portugal. So the Sun, on this scale model, is the size of a human cell, that's invisible, at the center of this pinhead, and the Earth is 100 times smaller, the size of a virus, and it's 2 millimeters away, and it's doing its little orbit every year, and the whole solar system is no bigger than my hand, in this room, and the nearest star is another human cell 250 meters away, and 250 meters is another star, and 250 meters is another star, and 250 meters or 100 or 150 or thereabouts is another human cell, and that's the solar neighborhood. And then the galaxy spans 3,000 kilometers. Okay, so galaxies are huge, huge things. Please don't ever confuse the Sun and the solar system with the Milky Way galaxy or any galaxy. Okay, that's the typical galactic scale. You'll also notice that all the stars that you see in the sky are very local to us. They're very local to us. Okay, I hope that you weren't confused by that. So, there we go. So that was our galaxy. You probably noticed in our little movie trip there, not all galaxies have the same shape as our own. There are other kinds of galaxies. So there are basically three kinds. Over here is the one that is our type. It's called a spiral galaxy. Has a disk with stars being born in it. It's currently fertile in that sense. Here's a galaxy which is called an elliptical kind of galaxy. Have ongoing star formation. It is infertile in a sense. The last stars that were born in that galaxy were probably 4 or 5 billion years ago. And the third category of galaxy, and this diagram doesn't illustrate it, these are much smaller. They'd be about this big, or this big, next to this. This is called an irregular galaxy, has no obvious structure to it. It has, in fact, a lot of stars being born within it. It's currently fertile. Now, so we now know a great deal about galaxies. There is much to tell you about them. I'm sorry, I can't have time, because I really want to zoom out and see a much larger scale. And so what I'm wanting to introduce now is the topic of how the galaxies are distributed throughout the universe. You already got a feel a little bit for that from that movie. They're dotted about, but let's approach the topic a little bit more formally. This is not, don't worry about not seeing too much on this image. It's sort of almost by design. This is just a chunk of the sky, and to give you some sense of how much sky, this would be the size of the full moon, were the full moon in the image. Of course, there's a coordinate system here, which is not unlike the longitude and latitude coordinate system for the Earth, but it's applied to the sky. It's the coordinate system astronomers use. And I hope you'll notice that in addition to the stars that you see, and this is actually in the constellation of Virgo. If you're familiar with Virgo, one of the stars here is, actually I can't even recognize it, I'm sorry, but there is one of the stars of Virgo's constellation in this picture. But also, you'll notice these fuzzy patches. Now, our eyes cannot see them. Our eyes are not sensitive enough. Although, actually, not by too much. Let's say we had owl vision. An owl is a nocturnal animal. If you could actually interrogate an owl and ask what it saw of the night sky, it would tell you, I mean, you know, if it could, that there were not only points of light, there were also fuzzy patches. These are the galaxies. They're quite there. They're not terribly small, but they're just too faint for us to see. If you turned up your ability to see, you would see them. And you can notice a few here, 1, 2, 3 big ones, a smaller one, a smaller one. There are many here, and in fact, if you catalogue them, this is where they all are, with all their different names. Now, of course, this is just the projection of them on the sky. My goal here is to try to describe how we've recently mapped their three-dimensional distribution. And to do that in volume, in 3 dimensions, we need to measure the distance to each one. We know its position on the sky. We need to measure the distance to it. Incidentally, I realize I'm making gestures here And I've also deliberately cut the lights. Can you see what my hands are doing? Can you see what I'm doing when I talk about distance? I don't want to be a complete black image here. So am I visible, folks? Yes, okay, thank you. All right, good. So in the last 15 years, so a lot of what I'm going to tell you is relatively recent, meaning a decade or two. There have been two enormous projects to measure the distance to 1 million galaxies. And this is just one of those projects illustrated here. I'm sorry my laser's not as strong as it should be. Does anybody have a more powerful laser beam that I could use? No. Okay. I thought my Alpine had one. But so here's the telescope that's used. Here's a person for scale. And here is I'm not going to describe it in detail. It's called a spectrograph, but importantly, it has about 640 fiber optics, which take the light from 640 galaxies and takes a spectrum of it. And in a manner in which I am not going to go into, it's possible to measure the distance to that galaxy using that data. And so this is the kind of maps that are produced. This is a patch of the sky that's about 120 degrees across. This is a big chunk of the sky. And this is just a flat image. This is what we see. And on it, all the stars have been removed. When all the light patches you can see here are 2 million galaxies covering this big patch of the sky. So it's difficult to show you three-dimensional maps of the whole volume. So what we tend to do is to take a slice, a narrow slice that's a few degrees deep, about 1 fist width deep, and a big slice maybe 60 degrees across like this. And then we're going to look at the galaxy distribution here, and we are going to be at the apex. We're going to be here, and out in this direction is distance, and this is across the sky, distance and across the sky in a thin wedge. This allows us to see the patterns. Thank you so much, that's great. There we go, now it's visible. So, this is one of those galaxy maps. The Milky Way is right down here, and we go out a distance of about 2 billion light years. I'm going to discuss the nature of light travel in a moment, but just basically what it means is the light from these galaxies out here took 2 billion years to get to us. It's essentially a measure of distance. Every little dot here, there's about 100,000 dots here. Every little dot is a galaxy. You'll notice that the pattern of galaxies is not uniform, but nor is it perfectly random. It's in between the two. Very, very interesting. And let me just show you a couple of things. First of all, our entire trip to the Virgo cluster, that first movie, took us no further than this circle. This is a huge map, okay, huge map. And you'll notice that there are regions which have few galaxies in. There are patches here with very few. These are called voids. But in addition, the voids are bounded by filaments and chains. So here are the lines or walls or filaments. There's a big one. And where these lines and walls intersect, there are very dense regions called clusters. Clusters of galaxies. There they are. So this is the nature of the cosmic topography, if you like. And as far as we know, once you look at a region about this big, it's not really statistically any different over here, or over here, or over here. The universe on larger scales looks like this. Not in detail, the individual voids and lines are not the same, but the pattern is essentially the same everywhere. So the universe is structured up to scales of about 100 million light years, and then after that, the universe is uniform in its distribution. A fascinating fact that I'm not going to be able to explain to you. It is known, but it can't be part of my story. I mean, if you want to talk to me about it later, you can, but there are reasons why that's the case. I just need to look at my notes, sorry, for a second. Where am I going in this story? Yes, okay. So that's the structure, the topography of the landscape on very large scales around us. Is there anything about it that's moving? This is a still image. This is the image that we got today, meaning a decade ago. Is there anything about it that's moving? And the answer is, you bet it is, fundamentally moving. So the third topic I'm talking about is cosmic expansion. I'm so sorry, I didn't actually mean to back up there. meant to hit that one, cosmic expansion. And so in addition to measuring the distances to galaxies, using a technique called the Doppler shift, it's possible to measure whether the galaxy is moving towards or away from you. Again, using the spectra of the galaxies, so you can actually extract the velocity of a galaxy. And I want to show you now what that pattern of velocities is. Here we have just another type of map. It's about half the size of the other, and it's filled in a bit more. These regions are blank because our own Milky Way got in the way. We couldn't measure the galaxies in that location, so it's not that they're not there, it's just that we couldn't measure them. But otherwise, you see the same patterns of voids and chains and walls. So this is a big region about 1 billion light years in radius, and the Milky Way galaxy, our galaxy, is at the center. And you'll notice I'm going to put on here velocity vectors of the galaxies. This is a slow velocity, this is a large velocity. So here's the pattern. You ready? There it is. And I want you to look at it carefully for a moment. So first of all, the thing to notice is that all the arrows are pointing radially away from us. Whoa, that's pretty interesting right there. Everything is moving away from us. There isn't a single galaxy that's ever been measured outside our local neighborhood that is moving towards us. They're all moving away from us. And secondly, you'll notice that the nearby galaxies are moving more slowly, and the more distant galaxies are moving faster. And furthermore, the velocity is in proportion to the distance. If the galaxy is twice as far away, it's moving twice as fast. If it's half as far away, it's moving half as fast. If it's 3 times as far, it moves 3 times as fast. It's a very simple rule. That rule has been given the name the Hubble Law, after the chap who first discovered it in 1929, Edwin Hubble, the iconic figure in modern cosmology. Okay, that was my history part, sorry. Now, you could be forgiven looking at this. You could feel either extremely proud, because clearly we're at the center of the universe and it's moving away from us, or you could feel extremely sheepish, because nobody wants to be close to us, they all want to move away from us. But neither of those reactions are appropriate. Although this myopically looks as though the expansion is away from us and we're in a privileged location, as in all good anthropological studies, you must ask the question, what do things look like to the other folks? What does it look like if I go to another galaxy and probe this same velocity field? So, for example, here we are on galaxy A, and here are the velocity vectors moving away from galaxy A in proportion to distance. What does this expansion look like to galaxy B? Now, to have a feeling for what that velocity pattern is, we must not only move to B, we must run along with B. And if we run along with B, I hope you can see that if we're on B and moving with it, at least this guy, we're going to be catching up. And so its velocity vector will not be as big as that, because we're now running with B, sitting on B. And similarly, if we're on B running in this direction, surely galaxy A will appear to us to be moving in the other direction. It's just a matter of perspective. Well, I'm going to now fill in all the arrows for you, and if you want to play with this using little vector diagrams and adding vectors, as you do in high school, not geometry, high school vector calculus, you can do it, and that's the pattern you come up with. Aha! Every galaxy sees the expansion away from it, identically to every other. This is a wonderful recognition that, in fact, there is no special location in the universe. The universe witnesses the same cosmic expansion. It is, in fact, a description of the fact that the entire universe is expanding uniformly. So there are 3 great conclusions from this particular velocity pattern. Every galaxy witnesses the same cosmic expansion. That's what I've just shown you. The corollary of that is there is no central location, or everywhere is central. As far as we can tell, there is no center, there is no edge. As far as we can see, this pattern is reproduced into the into the distances that we can probe with our telescopes. There's no center, no edge. Secondly, and very importantly, this particular law, if you track it backwards and ask where were the galaxies in the past, a galaxy that's this far and moving this speed, you can calculate, knowing the speed and the distance, you can figure out when it started its journey. It's just basically distance divided by velocity. That gives you the time interval. And it turns out to be about 14 billion years. But now think, and watch my hands for a moment. A galaxy that's twice as far away is moving twice as fast. So it covers twice the distance in the same time, because it's moving twice as fast. 3 times as far, 3 times as fast. So it gets there across that distance in the same interval of time. In other words, at one moment in time in the past, all of these galaxies were together in the same location. And as I've just said, knowing the distance and the speed, you can figure out that time. It's about 14 billion years. So this was one of the first pieces of concrete evidence that the universe started in a very different way, excuse me, a very different form to the form we currently see it in what is now called, of course, the Big Bang. There are now actually 6 independent pieces of evidence for the Big Bang, and I don't have time to go into them, so I'm just telling you that this is one of them. It's the form of the expansion. If you map it back, everything comes on top of itself at the same time. There's actually been a refinement, because you need to know whether the galaxies are moving at the same speed throughout their journey. In fact, they were moving faster initially, slowed down, excuse me, they didn't slow down, faster initially, they did slow down. They slowed down, and now they're speeding up. So when you allow for the change in speed, we can now figure out the age since the Big Bang. It's 13.7 billion years, with a 1% uncertainty on that. The third thing that you conclude from this is that the universe was denser in the past, and it will be emptier in the future. This is a wonderful conclusion. It's telling you that the universe as a whole is changing. It isn't always the same with an infinite past in some grand, stately manner. No, this system is changing, and it had a very dramatically different past. If you track it right back into the Big Bang itself, the universe was radically different in those early years. And that's a topic I'll pick up in my public lecture, which is tomorrow afternoon at 3 o'clock. The first 500,000 years of the universe's life. We're currently at 14 billion years, but a lot is known. It's possible to witness the first 500,000 years. So, indeed, that introduces me to that next topic, and that is, okay, so I've said that the universe was different in the past. Can we actually verify that? It's, obviously a common topic in academia, certainly is history, and how do you figure out what happened in the past? In the case of history, you have to work with what amounts to forensic information. You have to look at documents that were written, you have to look at artifacts that have come. In the case of astronomy, astronomers are incredibly lucky, because they can actually witness history directly without using forensic techniques. And the reason they can do this is quite straightforward. It takes quite a lot of time for the light to cross the universe from one object to another. So if we see a star which is, let's say, 10 light years away, that's about 10 times 13 trillion miles. It's a very big distance by human standards. It takes the light 10 years to get to us. So in our telescopes, we see that star as it was when the light set out, not as it is today. The light that hits our telescopes set out 10 years ago, so we see it as it was 10 years ago. 10 years is not much in cosmic history, but let's imagine looking further to a galaxy that's, let's say, 5 billion light years away. We see that galaxy as it was 5 billion years ago. We cannot have knowledge of it, of what it is like today. It's certainly there, and it's doing what it's doing, but we can't see that. What we witness is what that galaxy was like 5 billion years ago. So in order to study cosmic history, all you need to do is to build big telescopes that can punch through enormous cosmic distances. And de facto, whether you like it or not, you have to be witnessing history. You have no alternative, just because the light travel time is so long. So in a nice and beautiful sense then, telescopes are actually like time machines. They don't actually take us back there physically, but they do allow us to witness history. And so I just want to give you one example of a telescope that's enormously contributed to this part of the story. It's the Hubble Space Telescope. You'll notice that name again, Edwin Hubble. This telescope's named after this man who worked in the 1930s and 40s, 20s, 30s and 40s. And made major contributions to the study of cosmology. I didn't say that. Cosmology is the name of the subfield within astronomy which deals with the properties of the universe as a whole. Just give you a little bit of its history. It was launched 22 years ago now. It's an old telescope by modern standards. You may also have remembered it had some flawed optics to start with, and those were corrected by one of now 5 visits. It's in low Earth orbit, so it's possible to send astronauts up to change the instruments, to refurbish the telescope, to repair parts that are broken, and so on. This was the last mission. It will now be decommissioned, the telescope, so it'll continue until it breaks, basically. These guys were taking out an old instrument and putting in a new one. So this is the sort of game. Hubble has contributed in many areas of astronomy. I'm going to touch on the one that's our focus, and that is looking far away and back in time. So this is the basic story. Here's the Hubble Space Telescope. It looks at a small piece of the sky, points in one direction. Here's this piece of the sky. But let's not forget, in a small piece of the sky, it's actually a tunnel which goes long, long way away. So there you're looking across large distances, but of course you're looking back in time. So although this is the picture you get with galaxies in it, some galaxies are nearby, and therefore they are relatively old by galaxy standards, so they're adults, if you like, to use the human metaphor. But then further away, you'll notice these look tinier. Further away, we're in adolescence, and then yet further away, we're in children, and the tiny guys you can't even see on this picture are infants. We get an entire column, not only of distance, but really, we get slices through cosmic history, starting at infant galaxies and coming up to today. So I'm going to be actually showing you a number of graphs which plot all of cosmic history. This is an extraordinary thing to be saying to you. Do you see this diagram? It starts at the Big Bang, and there are 13.7 billion years, and here is today. And I'm going to be showing you graphs which track the properties of galaxies across all of cosmic history. There is no more to go. That's it. It's 14 billion years of it. We've reached back almost to the beginning. Now, so if you take this first 2 billion years, it's stretched up here, 0 to 2. The Hubble Space Telescope can see back, not to the beginning. It fades its vision around here. The galaxies are too faint and they're too far away, around 1 billion years. It can just see into the first billion years, but not the first half billion. And I'm going to deliberately postpone discussion of this region, which is the Big Bang itself, and the first few 100 million years until just at the end of this lecture, if I have time. But I want to focus on all of this part back to about 1 billion years after the Big Bang. So the Hubble telescope has looked in great detail at a few what are called deep fields. These are tiny patches of the sky. To give you a sense, here's the Big Dipper, and here's the full moon for scale, and here's the full moon again for scale, and this is the size of the region that the Hubble Space Telescope has looked at. There are 4 great deep fields. I'm going to show you the results of this. You'll notice that underneath there's an indication of sensitivity, how far you can see. This is the deepest. It's 12 times deeper than this one, and 3 times deeper than the most famous, which is called the Hubble Deep Field. This is the Hubble Ultra Deep Field. So I'm going to show you data from that because it's the furthest away. So this is a quarter of the Hubble Ultra Deep Field. It's the size, I should go back to my pinhead, it's the size of a pinhead held at arm's length. And if you look at that from the ground through a pretty large telescope, you will see precisely no galaxies. But the Hubble Space Telescope saw 10,000 galaxies underneath that pinhead. And we've no reason to believe that that pinhead is any different from any other pinhead anywhere in the sky. So if you want to know how many galaxies are visible to our current telescopes, although we've not actually seen them yet, you just take 10,000 and you multiply it by however many pinheads it takes to cover the sky, and that's about 220,000. And the total number is 100 billion visible galaxies in our visible universe. So this is a quarter of that little tiny field. And you'll notice there are some galaxies that are quite big, and when you measure their distances, which you can, this is 3 billion light years away. We're seeing that galaxy as it was 3 billion years ago, and it looks not unlike a modern galaxy. So 3 billion years ago, okay, adults are still adults. But that's not so true if here's one that's 5 billion years ago. But now let's look at this group. There's a distortion and interaction. That's 6.5 billion light years away, and this one's nearly 9.5 billion light years away. They're beginning to look rather different. And indeed, Now, those are not yet as far away as possible. If you want to look at the most distant galaxies, I've just picked a little region here. I'm going to blow it up now. It's filled with tiny little smudges. Each of those is a galaxy at enormous distance. The distances are possible to be measured approximately. All of these galaxies are smaller. This length here is 1 arcsecond. It's about the size of one of your 1 lira coins held about 5 miles away. They're very, very tiny. So these galaxies are smaller than that. And they have the brightness of about a single candle held on the moon. Very faint. So the telescope needs to stare at this patch for many, many days, actually, to detect these. And so let's take a look at those young galaxies. Here's a group of them. There are many of them that are found. And plotted on the same physical scale, here's 40,000 light years, here's 40,000 light years. It's the same scale. Here's today's sister galaxy, the Andromeda Galaxy, and these are the galaxies that are roughly 1.3 to 2 billion years after the Big Bang. So if you like, these are equivalent to about 7-year-old children if you have the metaphor that today is an 80-year-old adult. 7-year-old children compared to 80-year-old adults. And you'll notice they look nothing like modern galaxies. Just as human infants look radically different than adults, young galaxies look radically different. They're smaller. There are no clear, nice shapes, spiral patterns, and so on. And also, many, many of them are in collisions and interacting. Almost all of them are in the process of merging, in fact. So let's track some of those statements I've just made across all of cosmic history. So first of all, yes, they are very small. About 1 billion years after the Big Bang, the typical size of a galaxy is only 10,000 light years. But quickly, they grow. They grow in size by collisions and mergers. They're getting bigger. They're approaching today's size of galaxies. So this particular graph doesn't go up to today, but it does stop at 5 billion years after the Big Bang. And you can see there's a very unambiguous trend up in scale. Let me just see how much time I have here. I'm so sorry. I just want to make sure if I need to skip something, what I skip. So I'd like to show you a computer simulation of that early period. This simulation is going to span 14 billion years. This is a region of the universe which is going to become about 20 galaxies. And early on in the history, this is probably starting about 100 million years after the Big Bang. We're going to run forward in time. And you're going to see how a smooth region gravitationally coalesces in a hierarchical way to form many galaxies. Boom, there you go. Infant galaxies. We're already at 3 billion years after the Big Bang. 8 billion years. 10 billion years today. That's just formed a cluster of galaxies with 2 major galaxies in the center. And all of these little galaxies. But the most important thing that we've just been witnessing is this very early stage right here, where the first galaxies are condensing out and colliding and merging. Incidentally, of course, this is a computer simulation of the same sort of phenomena, putting in the laws of physics and trying to follow them on very big computers. That's a region I didn't tell you, which is 14 million light years across. And incidentally, that vision has suppressed cosmic expansion. So we did not witness the expansion during that. It was suppressed. Let me just show you a bigger region so you have some sense of the large-scale process. So this box is now 10 times bigger and ultimately will contain several thousand galaxies. I'm so sorry it's at its end. This is the beginning. You'll notice the early universe is very smooth, one of the primary characteristics. And again, I'm not showing cosmic expansion. This is a co-moving viewpoint. We're expanding with the box. Here we go. Boom. Very quickly. Structure emerges. The galaxies emerging. The other movie was a small region down here. We're now looking at the formation of the tapestry and the web. And you can see how it's formed quite nicely there, the tapestry. The web-like pattern was formed there. Okay. So, I've just mentioned that the little galaxies are merging, and as they do so, they sort of sweep clear the region around them. Of course, cosmic expansion is taking everything else further away, so only the one regions tend to coalesce to a single galaxy. And so, as you expect, perhaps, over cosmic history, this frequency of Galaxian collisions drops rapidly. And so, early, again, we have all of cosmic history here, from the Big Bang to today, and this is the percent of galaxies that are colliding. And so you can see that almost all galaxies in the first 2 to 3 billion years are in a state of Galaxian collisions, and then it drops. And so we're now, today, only 2% of galaxies are caught in collision. They've already undergone their collisions. And so now we can begin to actually track the change in the Galaxian sort of shape and size and properties over all of history. Here are a few snapshots. So the very earliest ones, about 1 billion. It's very difficult to see these things. They're very small. So there are, in fact, present-day counterparts to them, which we see in our own universe, and we can actually study those much more detail. Here's a lovely Hubble Space Telescope image of a nearby example of a dwarf irregular galaxy that's probably very similar, same scale to this one. You notice there's lots of young stars being born. There's a lot of gas that's present. It's a rather chaotic little blob, basically. But as we go along, here they are colliding and merging, and we don't really get decent, proper spiral galaxies until about 8 to 9 billion years after the Big Bang. It takes time to evolve the sort of structures we see today. So galaxy-galaxy collisions are a lovely topic here. I don't have too long, so let me just quickly show you. If you want to study galaxy collisions, you have to look nearby because you can't see things in detail so far away. The Hubble, manages to see that far, but with great effort. If you want to study galaxy collisions, you look at nearby examples. Here are 4 of them caught at different stages of collision. This is an early stage of collision and a late stage of collision. You can see how they come together. It's nicest, though, to follow these. And the whole thing takes 100 million to 1 billion years to unfold, so obviously humans can't watch it happen in a movie, but you can put it on a computer to simulate it. Here's a real galaxy collision, and here's the same one. This is a ground-based, this is Hubble Space Telescope image, and this is a computer simulation, what I'm about to show you, which tries to reproduce this particular kind of galaxy collision. So it starts with 2 galaxies far apart, and we're going to span, I think, about 1 billion years in about 30 seconds. So here they are coming in. The only physics, I should stop that there, I wanted to tell you that basically there are 100 million particles in this computer calculation, and they're just following Newton's laws. There's no exotic physics in this particular calculation. It's just Newton's laws, that's all. But there's 100 million particles. They represent stars. They follow the trajectory that stars would. So you start off with a spiral galaxy, and you make sure the initial conditions are right, and then you just let Newton's laws rip, and that's it. And a lot of computing time, but ultimately you see the patterns that emerge. Here we go. Boom. I'm going to stop it there, okay? If you remember, that's very similar to the appearance of those real galaxies that we saw. Now, obviously, this has been tweaked to match that, but nonetheless, you can see how it's possible to study the nature of galaxy collisions. Look at the centers merge now very quickly. There's a strong gravitational field in the center there, and the stars go on and spread about. And after about 1 billion or 2 years, this actually relaxes and ends up now, a bit later on, it ends up looking like an elliptical galaxy. What we've learned from these calculations is that the collision of 2 major spiral galaxies actually births an elliptical galaxy. So the history of some elliptical galaxies are, in fact, the mergers of major spiral galaxies. One thing that's very clear when galaxies collide, I only talked about the stars in that previous simulation, but gas is also involved as well. Galaxies have an interstellar atmosphere. I'll talk about that next lecture. And this atmosphere is involved in the birthing of stars. And one thing that really triggers that birthing mechanism is the collision of galaxies. And so, in ways which I can't go into and explain, when you look closely at 2 colliding galaxies, you measure enormous birth rates of stars. So in this particular galaxy collision, maybe 100 stars per year are being born. And I want you to compare that with the Milky Way's birth rate, which is less than 1 star per year. This is 2 orders of magnitude higher. In some galaxy collisions, there can be 1,000 stars per year being born. That may not seem much like to you or me, but after 100 million years and 1,000 stars being born per year, that's 1 billion stars, 10 billion stars right there. So this introduces another obvious possibility to you. If I've just told you the galaxy collision rate has dropped over time, what about the star birth history of the universe? What's that been like? So let's now have a look at the star birth history of the universe, and to give you some sense of what we're talking about, here is the human birth history in millions per year of the United States from 1935 to 2000, and here is the famous baby boom following the Second World War. And of course, the birth rate continues to rise. So what we're wanting to do is, for stars in the universe, what is the equivalent plot? Okay. So here it is. And the universe has a baby boom. It's wonderful. Shortly after the universe was born, it took a little while to get going, but after about 500 million years, and for the first 1 to 2 to 3 billion years, there was an enormous baby boom. This is the number of stars being born per cubic million light years, and so on. I mean, there's units to it. And then it drops off. And so today we're in really a relatively infertile universe. The universe is just calmed down. We're not in that wonderful state early in the history of the universe. Now, something else that you may not know is that when stars are born like this, there are many associated massive stars which are very bright. So if you look at the starlight history of the universe starts with an incredible flash of the Big Bang, which I'll talk about probably in my public lecture tomorrow. There's a dark age of 200 million years where no stars had yet formed. It was deep, deep darkness. And then, as the first stars began to form, we went through this period of extreme star brightness, and then ever since then, the universe has been becoming a darker place. So here's a lovely artist's impression of the 1 to 2 billion year universe, filled with small galaxies in states of collisions with supernova explosions going off and great shells of gas being blown out. Very active, wonderful. It's a bit like a fireworks display, but you have the crescendo at the beginning instead of the end. Okay, just reverse the classic human fireworks display. Okay, so I'm wanting to take this back to the earlier times still, and I just want to also see how long I have. How are we doing here? Do I need to... my watch just started a bit... 5 minutes, splendid. I might have time to do this. So now you'll notice that the timeline is actually the first billion years. And Hubble Space Telescope can see to here, so we can't see galaxies further than that. So there are 3 great aims for the near future. One is to see the first stars, which are being born around 200 to 300 million years. One is to see back to the pre-star era. This is called the Dark Age. And then the other is to see the flash from the Big Bang itself. Now, the first 2 have not yet been done. The third has been done very well. The Big Bang was so bright and such a flash that if you look far enough away, you can see it, which sounds like a remarkable statement. I'm going to flesh that idea out thoroughly in the public lecture tomorrow, when you can actually witness the birth of the universe. You just have to look very far away and you can see it. It's actually called the microwave background, if those of you have heard about it. So let me just have it. So one of the next great efforts is to look at this region with the first stars. And the Hubble Space Telescope's successor will hopefully do that. This is called the James Webb Space Telescope. You might wonder who James Webb is. He was more of a science administrator. He was one of NASA's top brass in the 1960s, and he persuaded the government, or persuaded NASA and the government, to make sure that science was actually a priority of NASA, not merely, I say merely, that's unfair, but not just human space flight. That actually the science, using space as a scientific access point, was important. It's named after him. It's gone through a few budgetary and technical problems, but ultimately it's on track now for a launch in 2018. And to give you some idea, here's the Hubble Space Telescope's primary mirror, and here's the JWST's main mirror. It's now 6 meters across. It's optimized for the infrared part of the spectrum because the starlight from the most distant stars has been so red shifted that it's now in the infrared part of the spectrum. So you have to look with infrared eyes if you want to see the deep universe. The intention of that then, one of the great aims is to see those first stars, the very first stars. For reasons I can't go into, they're thought to be rather different than today's stars. They're thought to be about 200 to 300 times the mass of the sun, 10 million times brighter than the sun, and they live less than 1 million years and die in supernova explosions. They're fabulous things. And they create the very first elements that then begin to season the gas that came out of the Big Bang. The other, to go deeper still, to see the dark age, so that this is now the quiet, cold gas that emerged from the Big Bang. The expansion has cooled the gas down. There's just very uniform gas clouds that are beginning to coalesce into the first stars. One needs to use radio telescopes to do that, and there's a next generation of radio telescopes called the Square Kilometre Array and LOFAR. These are huge instruments. This is currently being built. I know this looks completely pathetic, but you'll notice there are dishes all over Europe, and they all act coherently as a single telescope. This one will be probably built about 20 years from now. This one's currently being built, and the intention is to probe that first 200 million years and watch the beginnings of structure grow. And then, of course, that final part that I mentioned, the microwave background, is our view of the glowing gases coming out of the fireball of the first 500,000 years. And there's been much great study of that. This particular all-sky image, this funny oval, is in fact the entire panoramic sky, showing you the fireball's density and temperature fluctuations. It was very, very smooth gas back there, but there are slight patchiness. That patchiness will become the galaxies. So I'm hoping I just have 2 minutes now because I want to bring this whole story full cycle. We've gone right back to the 500,000 years after the Big Bang, and I started the lecture 14 billion years in, where we are today, with the structures of galaxies. What I'd like to do now is just to take us from here to here with a giant computer simulation, which begins with conditions that are observed here. So we take this slight patchiness and we interpret that, I mean, I should say correctly, we know that this is true, as slight density fluctuations, slightly denser regions, slightly less dense. This is a slightly denser region, and the blue is slightly less dense. This is going to become a void, a huge void between galaxies. This is going to become a cluster of galaxies. Where it's slightly denser, we're going to evolve into galaxies. So let's just take that initial condition. Here it is, about 200 million years after the Big Bang. You'll notice the universe is very, very smooth. There are slightly excess regions of matter and slightly less dense regions of matter. And this is a vast computer simulation that was done in the year 2002. It contained 10 billion particles, and it's mapping a region which you can see. I have to do this calculation quickly. This is about 800 million light years, so it's going to contain 2 million galaxies in the end. And let's run it now. So we're going to start off. Here we go. And gravity is already beginning to make the voids more void-like, and it's bringing gas and and stars and galaxies into regions. Here's going to be a big cluster is going to form here. The voids are already opening up. We've got all the filaments coming. We're currently about 8 billion years into the history. We're approaching today now. And you'll notice that we end up with a web-like tapestry, which when you analyze statistically is identical to the patterns of galaxies that we observe. This is a computer simulation. We've taken the conditions as observed off the microwave background. We've followed them using just Newton's laws. You don't need anything more fancy than that. It's just gravity. Forward through 14 billion years, and we've arrived at conditions which are eminently recognizable. There indeed were the clusters and the voids, and I would like to leave you with a wonderful, that computer simulation you can now fly through to see that tapestry in 3 dimensions in movie form. So this is the web of Galaxian distributions in today's universe. It's on a computer, but it's been evolved using realistic starting conditions that have been observed from the microwave background. And just so that you recognize there's more to the story I'm telling you. What's being depicted here actually are not galaxies, but a substance called dark matter. It transpires that most of the material in the universe is not the material that makes up you and me, the protons, neutrons, and electrons of atomic matter. It's another kind of matter called dark matter that we don't really know much about other than how it's distributed and some of its properties, enough of its properties to actually model them. This movie just zoomed into the central cluster of galaxies here. I'll leave that there And I would like to just remind you then, galaxies are primary units in cosmology. They are huge compared to the solar system. Remember, a pinhead compared to 3,000 kilometers. They fill the visible universe neither randomly nor uniformly. There's a web-like distribution of clusters and voids. There is cosmic expansion such that there is no center, there is no edge. Everywhere witnesses the same thing. And if you track back its origin, it was 13.7 billion years ago, currently with about a 1% uncertainty. You can access history directly using telescopes to witness currently, more or less all of Galaxian history, starting from about 1 billion years after the Big Bang till today. Galaxies were small, they quickly grow by collisions and mergers, and modern-day galaxies appear about 5 billion years ago. Pushing right back to the limit, we can see the cosmic microwave background. It is the fireball from the Big Bang, and it reveals the hot, smooth, early universe, but with seeds of structure visible, which you can then trace computationally to the modern-day universe. I'll leave that there, and we'll pick up the story of the first million years in the public lecture tomorrow at 3 o'clock, and then I'll come and talk more about locally formation of the solar system and the Earth and the origin of life in Wednesday's class.